Okay, so in today's lecture, this is lecture number 3, we are going to look into the combustion process. Now, what is this combustion process that we are talking about, and why is it important? Okay, combustion, as you know, is the burning of a fuel, a solid, liquid, or gaseous fuel. When it combines with oxygen at high temperature, it becomes an exothermic reaction, and it releases a lot of heat. A simple example is burning of wood or burning of paper. Burning of any fuel is a combustion process. Where do we use this combustion process? We use it everywhere in our lives. For example, the very cooking process every day that we do in our kitchen is a combustion process. Another area, two areas of our everyday life where combustion becomes very important is the engine that is there in our cars and our two-wheelers. That's where combustion takes place. And also remember that the power, electricity that we use every day comes by basically combusting fuels, particularly coal. There are also petroleum based thermal power stations where the power generation is based on burning petroleum based fuels. But in all these cases, one thing is absolutely common, and that is the combustion process. So ignition, a fuel, when it is set on fire or ignited, the condition becomes favorable for the fuel to catch fire, and in the process oxygen is mixed with the constituents of the fuel, and it provides heat, and the individual constituents of the fuel become oxidized. So let's take a look at this combustion process. It's an exothermic reaction accompanied by increase of heat. So for example, carbon plus oxygen gives you carbon dioxide. So when carbon burns, for example, coal, burning of coal is nothing but oxidation of carbon. The end product is carbon dioxide, and 97 kilocalories of heat is liberated. So if your fuel contains carbon, hydrogen, nitrogen, oxygen, and sulfur, these are the most common constituent elements. The corresponding products that you get are carbon dioxide. When you have complete combustion, sometimes it forms carbon monoxide when the oxygen supply is insufficient. Nitrogen gas, oxygen, molecular oxygen, sulfur dioxide if sulfur is present in your fuel, and water vapor, the hydrogen that is present in your fuel. Okay, so these are called as the flue gases, the byproducts. So what becomes very important is the availability of oxygen. Okay, so it becomes the most important parameter controlling the efficiency of a combustion process. So if you want complete combustion of a fuel, you have to ensure that the right amount of oxygen is present. For example, for every fuel, every gram of a fuel that you may take, there is a certain minimum amount of oxygen that is required for complete combustion. Any lesser amount of oxygen availability will make the combustion process incomplete, and that's what happens when for example, when you are doing a campfire or burning some green tree parts, incomplete combustion takes place, and that produces a lot of smoke, and smoke is nothing but carbon particles, and so that is an indication of incomplete combustion. And also the heat that is liberated is much lesser, the temperatures that you achieve is much lesser, and that is why an incomplete combustion results in a yellow color flame. On the contrary, when you have complete combustion, for example, what happens in your gas stove, you'll see a blue flame, and a blue flame indicates a higher temperature which is reached because of complete combustion, which means that enough oxygen is actually supplied to the burner. That's what it denotes. Okay, so even from a everyday usage standpoint, we can understand the importance of combustion and the importance of sufficient amount of oxygen. Another example I can give you where when we realize that enough oxygen is not available, we supply that extra oxygen. Where do we do that? For example, on an open fire using wood. For example, what they use in the villages, you have a primitive little stove in which you feed the fire with wood and other combustible substances. And sometimes when there is too much smoke, you want to set the wood on fire. So what you do is you start blowing into the fire, or you take a fan and you start fanning. And in doing both these things, when you blow or use a fan, what you are doing is you are supplying more oxygen so that the combustion becomes complete. Okay, so in our module, we have a way to calculate the minimum amount of air and thereby the minimum amount of oxygen that is required to completely combust a particular given fuel. Okay, so there are certain parameters or certain things that you need to consider before you proceed to calculate this minimum amount of air and oxygen. First thing is that air contains 23% by weight and 21% by volume of oxygen. What it means is, if you take 100 kilograms of air, out of that 23 kilograms will be oxygen. Similarly, if you take 100 liters of air, that is by volume, 21 liters will be oxygen. Okay, this is something you have to remember. So that's what is given here. Okay, so instead of liters, here we are using meter cube because that is the SI unit. Okay, another important thing that you need to note is that 22.4 liters of any gas at normal temperature and pressure has mass equal to 1 mole of that particular gas. Okay, so for example, oxygen exists in its bimolecular form, and so it is O2. A single oxygen atom weighs 16 AMU, so a molecule of oxygen weighs 32 AMU. So based on this relationship, 22.4 liter of oxygen will have a mass of 32 grams. Okay, something similar to this can be calculated for any other molecular gas that you can think about, for example carbon dioxide or nitrogen, but those things are not important. Molecular oxygen is the most important one here. Okay, so that's what is given here. 22.4 meter cube of oxygen at NTP will weigh 32 kilograms. Please remember that 1 meter cube is equal to 1000 liters. Now these are some of the considerations that you should be knowing by now. You have studied all these things in your lower classes as well. Okay, so let's look at how carbon combusts. Okay, so look at the equation, the chemical equation. 1 mole of carbon requires 1 mole of molecular oxygen to give you 1 mole of carbon dioxide. Okay, so this tells you that 1 mole of carbon requires a minimum of 1 mole of oxygen for complete combustion. Any lesser oxygen will result not in carbon dioxide but in carbon monoxide. So that is something that you want to avoid, because carbon monoxide is a poisonous gas. Okay, so when you look at it from a stoichiometric point of view, what it means is 12 grams of carbon. Why 12 grams? Because that's what 1 mole of carbon would weigh. 1 mole of carbon would weigh 12 grams. 12 grams of carbon will require a minimum of 32 grams of oxygen, and that will produce 44 grams of carbon dioxide. So what is it? what it means or what it implies is what is given here. 12 kilogram of carbon requires 32 kilogram of oxygen for complete combustion. So from that you can calculate how much 1 kilogram of carbon, how much oxygen is required. Okay, so that's 2.66 kilogram of oxygen for every kilogram. Okay, so look at this. 2.66 kilogram of oxygen is required. So 23 kilogram of oxygen is in 100 kilogram of air. So 2.66 kilogram of oxygen will be present in 100 by 23 into 2.66. That will be 11.56 kilogram of air. Okay, so what it means is that 1 kilogram of carbon for complete combustion requires 11.56 kilogram of air. Now we go to, now this is in kilograms, so that is in mass. Now by volume, 32 kilogram weight of oxygen occupies 22.4 meter cube of oxygen. Okay, so 2.66 kilogram will require 22.4 by 32 into 2.66, which will be 1.86 meter cube of oxygen. This is pure oxygen. So how much of this pure oxygen will be present in air? That is dependent on the factor that 100 liters of air contains 21 liters of oxygen. So you simply multiply it by a factor of 100 by 21. So that will give you 8.87 meter cube of air. So in other words, 1 kilogram of carbon requires 2.66 kilogram of oxygen, which is present in 11.56 kilogram of air on the surface of the earth. Okay. Similarly, 1 kilogram of carbon requires 1.86 meter cube of oxygen, which is present in 8.87 meter cube of air. Okay. Now, based on this understanding, we will be solving some numerical problems, which I will show you soon. Okay, now we will look at the combustion of hydrogen. The combustion of hydrogen chemically is shown this way. Two molecules of hydrogen or 2 moles of hydrogen gas requires 1 mole of oxygen to give you water. What is on the product side, don't worry about this value, because what is important is this. Okay, so which means for every 4 gram of hydrogen, 32 grams of oxygen is required for complete combustion. So that's what is shown here. So from that you can find out how much oxygen is required for a given amount of hydrogen present in your fuel. Now, another important, when you do the calculation, a factor that is equivalent to oxygen by 8 is removed from the total oxygen present. That is because if your fuel contains oxygen, that oxygen itself is used for some of the combustion process. The oxygen does not have to come from the external air, but it can be supplied from the fuel itself. Okay, so if you know how much oxygen is present, that can be subtracted from the total oxygen required for hydrogen, and that will give you an accurate estimation of how much external oxygen is required for combusting hydrogen. So that is equal to 32 by 4 into hydrogen minus oxygen by 8. Okay, now let's go for sulfur. We are not considering nitrogen, but because under normal conditions, nitrogen is not going to combine with oxygen to give nitrogen oxide gases under normal conditions. In a petrol engine or a diesel engine, it does combine, but those are abnormal conditions. Okay, so that is why I am telling this. Okay, under normal conditions, if your fuel contains nitrogen, it will be converted into nitrogen gas where there is no oxygen present. So oxygen is not consumed. That is why we are not considering that. Okay, now let's look at combustion of sulfur. This is more straightforward. 32 grams of sulfur requires 32 grams of oxygen. Very simple, straightforward relationships, linear relationship. Okay, so what happens is, if you have 1 kilogram of sulfur, 1 kilogram of oxygen is required. Okay, so putting all these things together, we have a very simple convenient formula in our hand, which is given this way. The theoretical oxygen requirement for the combustion of carbon, hydrogen, sulfur is given by 32 by 12 into carbon, that is the amount of carbon in your fuel, plus 8 into hydrogen amount minus oxygen amount by 8, okay, plus the sulfur amount. All of these expressed in kilograms. So carbon amount is expressed in kilograms, hydrogen amount is expressed in kilograms, oxygen amount is expressed in kilograms, and sulfur amount is expressed in kilograms. Okay, if you express all these things in kilograms, you can actually find the total amount of molecular oxygen required in kilograms for complete combustion. So why should we do this calculation? Let's imagine that you are working for a national thermal power corporation, and you are setting up a combustion chamber for producing electricity. Okay, it is not simple burning of a coal. Remember that coal will be burnt in huge amounts. Okay, so you have to design a combustion chamber where tons and tons of coal is burnt simultaneously but absolutely efficiently. Okay, if you do not burn it efficiently, there are two problems. One is the maximum calorific value of the fuel will not be obtained, and so you will be wasting the fuel. And second thing, it will result in formation of lot of carbon monoxide and carbon soot, both of which will affect the environment in a big way. So that is why perfect 100% or as close to 100% combustion of the fuel is an absolute essential. Okay, that is why we are doing this exercise. Once you find out the amount of oxygen in kilograms, you can convert it into amount of air that is required in kilograms, and also you can express that as oxygen required in liters or meter cube and air required in meter cube. Okay, so in the next video I'm going to show you a couple of numerical problems, how using this expression we can solve some numerical problems. Okay, so I will see you in the next video. Hello students, this is lecture number 4, where I'm going to demonstrate how to solve a simple numerical problem based on the expression that we obtained in the previous class for the theoretical oxygen requirement for the combustion of a fuel. Okay, so the expression that we obtained in the last class was this. This is something you need to remember. 32 by 12 into amount of carbon plus 8 multiplied by hydrogen minus amount of oxygen by 8 plus sulfur amount in kilograms. Now all this carbon, hydrogen, oxygen and sulfur are to be calculated in kilograms or in grams. Okay, in order to proceed to calculate the theoretical minimum amount of oxygen required. Once you find the oxygen amount in kilograms, then you can also convert it into amount of air that is required in kilograms, and also amount of oxygen and air required in liters or meter cube, that is the volume. Okay, so all these things can be done. Okay, so let's solve a problem. So look at the problem number 1. This is a typical problem we keep asking every semester. Okay, very simple. By now you might have realized that all numerical problems in engineering chemistry are straightforward, simple problems. nothing complicated. All you have to do is just remember the uh, the expression, the mathematical expression that is required. Okay, no integration, no derivation, no sophisticated functions, no algebra, nothing. Okay, very straightforward ones. Okay, very linear expressions. Okay, so let's look at the question. A coal sample has the following percentage composition: carbon is 87 percentage, hydrogen is 4.5 percentage, oxygen is 3 percentage, sulfur is 0.5 percentage, moisture is 3.5, nitrogen is 0.5, and ash 1 percentage. Okay, the question is, calculate the theoretical minimum weight of air required for the complete combustion of 1 kilogram of coal. Okay, so how do we proceed solving this problem? Okay, the first hint is convert all percentage values of the elements into kilograms first. My suggestion is go for grams. That will be a little easier, because you will not, the chances of making a mistake comes down if you do it in grams. Even though here in this case I have shown it in kilograms, that's my suggestion. What does this mean? Okay, so if you have 1 kilogram of coal, how much kilogram of carbon will be present in it? Okay, so since it is 87 percentage, it will be 0.87 kilograms, or if you convert it into grams, it will be 870 grams. Okay, similarly, if you do the same conversion, hydrogen will be present in 45 grams, 30 grams of oxygen will be present, and 5 grams of sulfur will be present in 1 kilogram of coal. Now what about these three parameters? Moisture is just water. Okay, now water will not be converted to water, so it stays as it is, so nothing happens. You don't require oxygen for a reaction of moisture. Nitrogen also does not require any oxygen, and ash is uncombusted substance, so this also does not require any oxygen. So you need to calculate oxygen content required only for these elements. Okay, so how do you do that? So here you substitute the values, the corresponding values. So 32 by 12 into carbon amount, which is 870 grams, plus 8 into 45 grams of hydrogen minus 30 grams of oxygen by 8, plus 5 grams of sulfur. Okay, so if you solve this, which is very straightforward, shown here, you will get 2655 grams of molecular oxygen. Okay, so the air required will be very simple, 100 divided by 23. Okay, so 11.54 kilogram of air is required for complete combustion. This is the minimum amount of air. What it means is that for the complete combustion, you can supply higher amount, excess of air, but you cannot supply an amount lesser than this. Okay, otherwise incomplete combustion will take place. Here is another problem for you to consider. 1 kilogram of a fuel oil has the following composition: 90% carbon, 6% hydrogen, 2.5% sulfur, 1% oxygen, ash 0.5%. Calculate the quantity of air required for the complete combustion of 1 kilogram of fuel by weight and volume. Okay, so I have already shown you in earlier class, in the last lecture, what is the relationship between mass of mass of oxygen and the volume that it occupies. Remember, 32 kilogram of oxygen occupies 22.4 meter cube of space. Okay, so based on that you need to do. I'm not going to demonstrate it. You guys try it. You are all engineering students. You should be able to do it. Okay. Similarly, also do this problem. Okay. Now in examination, if we forget to give you how much fuel is taken, consider it as 1 kilogram. Otherwise, sometimes we also give you how much fuel is taken, so just multiply by that particular amount. Okay, by using this simple expression you can easily do this numerical problem. Okay, thank you. So I'll see you in the next video.